Hi, we will wait for several minutes and start our seminar.
Okay.
Well, let's start. And today we will talk about summarization task, namely abstractive summarization and extractive summarization. So I hope you were told a little bit about summarization at the lecture. So I'll briefly remind you the main ideas of summarization, the main idea of a task, and so on and so on. So summarization is usually divided by two parts. So it's extractive summarization and abstractive summarization or abstract summarization. So in case of extractive summarization, we have to extract several sentences or maybe even several words, whatever, to obtain some informative summary. In case of abstractive summarization, we have to generate a small, for example, a small paragraph or a set of sentences which describe our text in a better way. So the main difference with extractive summarization, it's something like span detection task or something like that. And abstractive summarization, it's a generation task. So it's on one hand, it's more interesting and create better text. Well, in good case scenario, but on the other hand, it's harder task because there are a lot of problems with text generation, as you already know. So again, let's install all the necessary libraries. And first of all, let's look on metrics, what we can use for summarization task. Again, because of different input and output, different from the usual classification task or named recognition task, we have to use some another type of metrics. Moreover, in most cases for abstractive summarization, we don't have we have some reference summary, but we always suppose what in most cases we can generate a slightly different summary, what also will be good enough. So it's could be a very simple thing. For example, if you have some big text, and if you, for example, give it to several peoples, well, all of the people likely generate a good enough summary, but with summary will differs a lot between different people. But nevertheless, it will be quite informative. So we have to define some metrics what we can use to evaluate quality of our summary. The most common metric is ROC score. So as one can see, we can have ROC1, ROC2, ROC-L, and ROC-L sum. So ROC1, it's F1 score for unigrams. So ROC2 is F1 score for bigrams, and so on and so on. We can define ROC3, ROC4, and so on and so on. But usually we stop with ROC1, ROC2, and ROC-L, what stands for the longest subsequence between our prediction and the reference summary. So in case of ROC1, we calculate precision and recall by unigrams between these two summaries. And after that, calculate F1 score for precision and recall. So it's quite simple. In case of ROC2, we do the same thing for bigrams. In case of ROC-L, we try to find the longest common subsequence between our prediction and our reference summary. So in this case, it will be, well, allowed reading the Hunger Games. So it's the longest subsequence in both summaries. So this is the most common metric for abstractive summarization. And now let's look at how we can do this with well, well, our favorite Hugging Face library. So again, install it, import all necessary dependencies, and let's look again at this task. So this is a screenshot from Hugging Face Spaces, where everyone can look at this task in action. So again, we have one long article, in which case, in this case, it's an article about the Eiffel Tower, and we want to extract a short summary with some informative, of some useful information. Well, we will use an XSum dataset. So it's contained again articles from BBC site and contain some one or several sentences summaries, what are usually articles headings. So we will use T5 small, well, because it fits in our GPU RAM, and it's quite efficient. Again, we will install some in our libraries, and again load our dataset and load our metrics. Now we will look at one more metric for abstractive summarization called Meteor. This is quite a recent metric compared to ROOC. And it was shown what this metric have higher correlation with human judgment about summary. So again, in abstractive summarization, we have a lot of problems with metrics because we want to, well, somehow say how good our summary is. And because we can generate a lot of different summaries, and for example, different summaries could be all good enough, we want to have some, well, good enough metrics to measure with. So it's well, it's a big research problem, and well, everyone can participate in that. If, for example, we have any one of you have some ideas of how to, well, adopt some novel metrics for summarization, it will be great. Our data almost loaded. So let's wait a little bit more. When again, we can, as usual, we want to look at our dataset structure because we want to know what fields we have in our data set, what text we have in our data set, and so on and so on. Maybe there is some outliers, there is some strange text, and so on. So we want to quickly check it. So we simply look at our text when our data set finally loaded. And we finally loaded our dataset, and let's look at its structure. Again, nothing unusual. We have document, we have summary, and have some ID field. And let's look at one element from our dataset. Again, nothing unusual. We have some long enough text, which is some article from the BBC News site. We have some summary, what usually are, heading of article, maybe a lead of article, something like that. In which case, it doesn't really matter. So we subsample our dataset because we want to train our model, really fast. What we couldn't achieve if we will train on 200 Ks of our text. Again, let's look at some more random elements from our dataset to check if we have maybe some strange text, some different domains, maybe. But again, nothing unusual. It's all common use. Look like we haven't some strange entities. Well, we have some strange entity in here. Look like a typo or maybe some decoding problem. But again, it's could affect a lot at our model. Well, everything looks fine. And again, a few words about our metrics. Well, one more time, a definition of a ROC matrix. So it's simply one score from n grams, unigram, bigram, longest subsequence, and so on. Here we can look at with specific implementation of a ROC score. So we can see what we can define the type of ROC score we want to calculate in our case. For example, ROC1, ROC2, and so on and so on. And we also have some different examples. So as we can see, when we have the same generated summary and reference summary, we will obtain the highest ROC score for all types of this metric. But again, as we expect. So this is where algorithm how to calculate an hour metric called Meteor. So nothing unusual. We calculate precision, we calculate recall, both of them by unigrams, and after that we calculated weighted F1 score with some additional coefficients. So we want to use our precision and recall scores with different weights. And after that, we again add some smart reweighting and finally calculate this score. what's the main point of this modification? Well, there was a paper about this metric, and in this paper it was shown that these new metrics have higher correlation with human judgment about generated summaries. So this is one of the problem of ROG score. What is this metric? Not very correlated with human judgment about generated summaries again. And well, the meteor metric is one of the ways to solve this problem. Again, this metric, of course, doesn't have the best possible correlation of human judgment, but it's quite high, about, well, as I remember, about 0.9, maybe 0.8, something like that. And again, we can calculate our ROG scores and meteor scores for some, well, test summary. So again, we can see what we have a lot of similar unigrams in both summaries, but again, we can see what our generated summary is very, very different from the reference summary. So in this case, we have to say what we really hated reading the Hunger Games, and our reference summary means the opposite. So I loved reading the Hunger Games. But we can see what our generated metrics is quite high, except maybe ROG 2, because there are not so many big runs. So it's again one more point about what we don't have some, well, good and reliable metric for summarization task. So it's still an open research question. And even with new one metric shows quite a high score, what's again strange, because we have opposite meaning for our generated summary. But again, all these metrics calculated by some unigrams, bigrams, n-grams, and so on. So we have quite a big overlap in, well, longest subsequence, for example, in unigrams, of course, and even in bigrams as well. So, well, let's move to our processing part. Again, nothing unusual. Import our tokenizer, try to tokenize our sentence. And again, nothing unusual. One interesting thing, because we want to use some T5 model and we want to make summarization task, we have to add some keyword summarize before our sentences, before our log context. So let's include in our preprocessing pipeline. And here, again, we have sequence-to-sequence generation task. So we want to define our maximum input length and our maximum target length. So we don't want to generate some, well, for example, very, very long summaries, because, well, the main idea of summarization is to generate shorter text when we have as an input. So we want something brief, something informative, and something quite short. So again, nothing unusual. We simply tokenize our texts and get some attention mask. Well, again, everything as usual. And in which case, we have some reference summary as a label. So apply this function to all dataset. Again, all of these results will be cached by the dataset library. So if you want to do it in the next step, we can simply load the cached version of our dataset, and it will be much more faster. And again, let's move to fine-tuning for our model. well, as it was said before, in most cases, fine-tuning and preprocessing text with Hugging Face is always similar. So we know what we have sequence-to-sequence task. So we import some classes for sequence-to-sequence task and simply use one more time define training arguments. Mostly it's contain arguments like learning rate, batch size, and so on and so on. But we will have some additional argument predictive generate. So we want to predict our new summaries. And again, to speed up our training, we will use half precision training. So it's supported with this type of GPU, I hope. So we have, well, I suppose that we have something like VSTOR, so it should support half precision. And well, let's move to the next part and finally train our model. Well, before we train our model, we want to define some function for calculate aforementioned metrics, namely Rogue, Meteor, and so on and so on. And for that, we want to avoid calculate our metrics on paid-in tokens, as usual. So we want to replace it with something empty. And finally, well, we move to training part and start train our model. So we can wait a little. And after that, we will, as usual, evaluate our model, look at model's predictions, and, well, maybe even look at generated texts. As in all previous tasks, we can simply wrap our models and our tokenization, preprocessing part, and so on in some pipeline, what will be easily called from standard Hugging Face functions, as it was done before. And after that, we will also look at some summarization for Russian language and also look at summarization with our task, namely extractive summarization, which is, well, kind of simpler, but, well, generated summary with extractive summarization usually looks something worse when abstractive summaries, cause in case of extractive summarization, we simply extract some, well, the most relevant sentences from the text. So in some cases, it will look not very natural, for example, as abstractive summarization. But on the other hand, the extractive summarization task is somehow simpler because we don't need to generate sequences. We could simply, well, choose several sentences from our input document, and it's much more simpler. It's much more faster when to generate some short summary with abstractive summarization. And moreover, in case of extractive summarization, we didn't have some abstractive summarization specific problems, for example, like hallucinations and something like that. So again, we will also talk about hallucination and abstractive summarization, which is again still an open research question in this task. So it looks like our model is still training, so we can speak a little bit about hallucination. So in case of abstractive summarization, we in every generated summary, we want our summary to be informative and don't contain some unuseful information. And of course, we don't want to our summary to contain some erroneous information. So we don't want, for example, from our summary, from our model, for example, let's suppose we train our model to summarize the news. And, for example, we told our model some article about how Elon Musk buys, Twitter. And we don't want to our model to generate some summary which says what Elon Musk bought, for example, Facebook. It will be some kind of mistake. It could have a very high cost. For example, if we use our summaries in production, for example, for some decision making, something like that. So we don't want from our model some mistakes like that. Or maybe, for example, our model can generate some summaries using not the input document, but some knowledge from pre-training stage. For example, it could replace some people's birth date or maybe death date, something like that. So it's an interesting question how we can detect some hallucinations and how we can remove this hallucination from our generated summary. Of course, in most cases, we cannot remove this hallucination, but in the first case, we want to, at least detect these erroneous summaries and somehow filter it. Our model is finally trained, so let's look at our metrics at validation set. And we can see what we have some not so high validation metrics. We can see some average length of generated summary, some metrics that we discussed before, different version of ROC and Meteor. So again, it's quite low. So I recall that one is means we have an ideal summary. But again, we will train our model for half an epoch, and again, we can definitely say what it will not enough. So if we will train our model for a little bit more time, we'll obtain much more better metrics. So let's look at the generated summary for one of documented from predation split. and we can see what probably our document should tell something about some new film and the trailer of this new film, and well, most likely this is some series of films. So let's check it and look at our input text. Well, we can see what this is a text about trailer to one of Star Wars movies, and it's discussing some details of this trailer, and looks like what this is not well, the most useful information from this text. So again, it's one more problem with summarization. Well, it's different human judgments. So maybe someone find the most interesting part of his text is something about the waiter and, well, his trademark heavy breathing, or maybe someone else decide what the most interesting and informative part is something about, for example, Star Wars celebration event in London, or maybe the name of a film, A New Hope, and so on and so on. So it's again, it depends of what we want from our summary. So one more time, we have some pipeline for summarization, as we have similar pipelines for all our task and Hugging Face. So here is nothing unusual. Load model, wrap it inside pipeline, and run it over our documents. So here we will use some default model, which is distill bar, and run it all over our document and look at the generated summary. Again, we can set the minimum length of our generated summary, because, for example, we don't want a very short summary. We will say something like, this is the text about the film. Okay, you'll know it again already, but we want something, well, more informative. And here we can see what with better trained models will unsurprisingly get better results. So our text said what we have some different trailer for this new film, and well, date of release of this trailer, date of release of the film, and so on and so on. So it's quite short and quite informative. Well, anyways, it looks much better when this one summary. Well, now let's try to summarize some Russian text. Look at text from gazeta.ru, well, gazeta.ru news site, and try to summarize some Russian text. So again, there's no such difference between Russian summarization in Russian and summarization in English, but let's look. The next part will be devoted to some techniques for detecting hallucinations. Unfortunately, I suppose what we couldn't run this library on Colab, but well, we will try. Well, let's wait a little bit while model for Russian summarization will be loaded. So while the model is loading, we can watch it. We can look at our text, and we can see what this is some kind of news article about well, vehicles, about laws, about some well, petrol taxation, and so on and so on. So, well, I suppose what we want to see in our summary some useful information about which tax is increased and well, how it increased. So it looked like it's the most interesting and informative part of this big text. So let's wait a little bit. Again, as one can see, the generation task is quite slow. So again, it's one more problem for abstract summarization. What we want to generate some summaries, but in most cases it's kind of slow because we want to generate it token by token, as we usually do it in some generation tasks, like it was in question answering or an MT and so on. So if we want to use some well, abstractive summarization in production, we always want to think about how to speed up the generation process. Well, let's see at our summary. Well, again, it's talking about vehicle petrol taxation and how to increase taxes and which type of vehicles will suffer more from this new law. So it looks like what summary is quite consistent in which case, in this case. So let's move to hallucination markup. Again, I suppose we couldn't run this in Gleb due to memory limit. So let's simply look at two kind of summaries. So here we can see the common situation for hallucination. We have some article about Lionel Messi and well, told when it was born, when he was born, where he was born, who is what he is doing, and so on and so on. So an article says what he's a professional footballer, and he was born in Argentina, and he was born in 1987. But our summary told us what he is a Spanish footballer, and he was born at 1997, which is obviously some kind of wrong summary. So it's one of the most common cases of hallucination. So we want to detect these mistakes and maybe somehow fix it, or maybe simply somehow mark this sentence and told what this sentence contains some factual errors. So how we can do it? We can run something like named entity recognition, for example, for our text and our summary, and compare some named entities. So as we can see, in this case, Argentina and Spain, and as well as date of birth is named entities. So we can simply compare entities from our input article and our generated summary. And well, with this simple approach, we already can say what we have some strange difference between a generated summary and input article. Whereas some our approaches, for example, we can try to extract some triplets of words. For example, in this case, we have some triplet like Lionel Andres Messi is an Argentine professional footballer. And here we can extract the almost similar triplet, what contain word Spanish, and well, these triplets are not the same, so we could have some factual mistake. So one more time, it's an open research question: how to stable, efficient, and well, how to robust and efficient detect hallucination and even fix it. So, well, let's move to extractive summarization. It's somehow similar task, but here we want to simply extract our sentences. So the main idea is following: we have some set of documents. In each document, we have some set of sentences, and for each of these documents, we can extract some the most relevant sentences and say what, well, these sentences is more likely to contain some key information about text. As everyone can see, this is not the best approach, because, for example, for some texts, we wouldn't have some key sentences what contain the main information about text. For example, this approach could work very good, for example, for news articles, because most of the news articles, for example, some maybe some even bigger articles have the same structure, and this same structure usually starts with some lead sentences what briefly summarize the main idea of a text, which is text about, what it will told us about, and why we should read it. So, for example, for some cases, we can simply extract some some first sentences of our text. But in some cases, we simply don't have some key sentences, so our model will have to improvise and extract something like, well, the most interesting, but probably not the best sentences. Well, let's load our dataset. Again, it's CNN News. It's one more common dataset for extractive summarization task. So we will load it, we'll extract it, and look at our summaries. So again, it's told about some news about Twitter. So again, it's well, standard news domain. So nothing unusual. Well, let's load some package for computation, because we want to split our documents to sentences. Again, because we want to extract some most useful and important sentences from our documents. Well, the main advantage of extractive summarization is what we can use some very, very simple approach. So, for example, we have we could simply vectorize our words, combine it into some vectors for sentences. Well, after that, calculate something like TF-IDF score and obtain again some high-level representation of our document. And after that, well, simply simply make some ranking our generated vectors for sentences, and well, simply use the sentences with higher ranks. So, for example, now we will look at text rank algorithm, which is, well, the same as the page rank algorithm, but is, I suppose, you were told about at some programming course, maybe, or maybe at the course of graphs, I suppose. Did you have the page rank algorithm at previous courses or not?
Well, I can't recall, to be honest. There was a lot of information, so maybe yes, maybe no.
Well, okay, so we'll briefly recall this algorithm in this case. So as it was said before, we will simply split our documents on sentences, calculate vectors for our sentences using Gleb vectors and TF-IDF. This was done before in previous seminars, and after that we will try to imagine our documents as some kind of graph, which have some which have some vertices as a sentence. So each vertex of our graph is a sentence from our document, and we want to somehow weight our again, the main idea, what we want somehow to weight our vertices in our graph to find some most important vertices. So vectorize all our texts, and we can define somehow a similarity matrix between our vertices. And this similarity matrix could be used as an edges for our graph. So here we simply calculate Gaussian similarity, but again we can use maybe some more advanced metrics. We can, for example, calculate some more rigorous distance. Euclidean, for example, but in this case, Gaussian similarity is better than Euclidean distance, I suppose. But we can somehow modify our distance to a specific task if we want to do this, of course. So, this is a brief description of text rank algorithm, which is the same as a page rank algorithm, which were used a long time ago by the Google search engine, and now the page rank is widely used in some citation graphs, for example, in science, when we want to find the similar authors or the similar articles in the space of all articles what we have. And again, it's also quite an interesting task because we, for example, could use some abstract information from our papers to calculate such a graph. And let's return to extractive summarization. And so it's a simple iterative algorithm. We have some hyperparameters, for example, d, which is damping coefficient. With our parameters, it's quite simple. So we have our similarity matrix to represent our graph. We have some hyperparameters, and we simply calculate our PageRank score for each of vertices until our calculation process doesn't converge. So we simply calculate this thing inside our loop and wait while our some conversions criteria will be fulfilled. So in which case we can see what our convergence criteria is difference between page rank scores on current iteration and previous iteration. So when we have a very small difference in our page rank scores, we can say what our scores are, well, some kind of robust to new changes, and we can stop modifying these scores. So, well, we simply start from zero matrix and well, calculate with thing inside the loop. So it's quite simple, except we have some, well, rigorous matrix multiplication to speed up this whole process. So let's calc our scores. Well, again, we don't define our CSR matrix because we don't import this thing. So again, it's great algorithm, but of course, there will be some issues if we want to run it, well, for example, on Google-like data, if you want to make somehow with scoring for, well, for billions of sites in our search engine. So there are a lot of tricks how to speed up this algorithm, but in our case, we have simple small data sets, so we don't do anything of that. And well, we obtain some ranked sentences from our text. We can print it and look at it. Well, here we print all of the sentences, so we can look at all of the sentences and well, check what is our text about. So again, something about of Twitter. So again, it's something like about Twitter, about economics, and about some news. And then now we can look at the most informative sentences according to the page rank score, no text rank score. Well, so if we read our summary, you could think what our text is about some, well, some details of work in Twitter, some details about Twitter. So, well, Twitter is a tech company. Well, there are not a lot of diversity inside of Twitter, and well, we can check it. And yes, look like our text is told us something about that. So we could see some percentage of women and men inside of Twitter. So some words about diversity, some words about well, about some modern problems of Twitter. And again, of course, we don't have to write some commonly used methods like text rank. So we can simply import our text rank algorithm and well, calculate almost the same scores and obtain almost the same results, but much faster. So, because in this library we will have much more efficient implementation, of course. And we can see what we have with similar scores. in our implementation and in the library implementation. And we can look at results one more time. So we will save our summaries and compare. Well, and now we can evaluate our saved summaries, what we generate with text rank algorithm, with our previously mentioned metrics, namely Rogue and Meteor. So again, we can see what we have, not so high metric values. So this means what where text rank scores is not so good decision for extractive summarization. Maybe we extract not best sentences for our document, or maybe we don't have good enough vectors for our documents, which is more likely. So as we could expect, the text rank algorithm heavily rely on generated embeddings, which is used for score calculation, and maybe not only on the generated embeddings, but more on similarity matrix. And again, we can suppose that we have not good enough vectors, our embeddings, or maybe we don't have good enough similarity matrix. Because the Cassin similarity is, well, it's a good enough measure, but for example, it's proven what it doesn't work good, for example, for BERT-like models. Well, of course, in our case, we don't have a BERT-like model, but again, maybe there is some better ways to calculate similarity matrix for text rank algorithm. Again, we have our implementation of text rank because it's a very common algorithm, which is stored in again very popular library GenSim, what we were looked at our previous seminars also. And we can try to summarize some poetry. And of course, as anyone could expect, some poetry is very hard to summarize because there are a lot of metaphors, or there are a lot of some, well, some unclear sentences, unclear words, and so on and so on. So it's highly ambiguous, and moreover, well, the poetry, it's a very strange domain for summarization because, well, the main idea of poetry is to read all of this text by yourself in full version. So summarize the poetry, it's kind of strange task, of course. But maybe we want to do this. So let's try. And we can see what this is some text about rice pudding. And the main idea of this text is about the Mary Jane who don't want to eat her rice pudding, her breakfast. So, well, she simply don't want to eat it. That's all. So it's hard to summarize. So we get a sentence what, well, she really don't want to eat her rice pudding. And well, even if she will promise some dose or something else, she still don't want to eat. Well, maybe she simply doesn't like this responding. So if we want to extract the summary in one sentence, it will be something like that. It's well, quite uninformative, so it's have no meaningful information about the text. So by this sentence, we couldn't understand anything. Well, but we can define different measures of our summary generation. So we can control the length of extracted sentences, the number of extracted sentences, the ratio of extracted sentences, and so on and so on. Well, and again, for example, we can use this implementation for our previous CNN dataset and calculate again our metrics to check if we have a better implementation inside the GenSim library. So it could be done as your additional homework task if you want to do it. And of course, we can use some more advanced model for extractive summarization. For example, we can use BERT. It's kind of simple. We simply want to mask some of our sentences and, well, for example, define spans, which contains the most useful information for our summary. Well, let's try to run this version, but I suppose it will be some kind of very, very old version of PyTorch. So, well, yes, looks like we couldn't run this version of extractive summarization for BERT. So let's try another version. I suppose it will have something like that. Well, yep, it's look like we have another version for BERT extractive summarization. Let's try this one. Again, let's wait a little bit while our library is installing. To sum up, we'll have almost the same results for repository, of course, but with the usage of more recent neural networks, we'll obtain better results by the ROG score or Meteor score, whatever. So, of course, it's better to use some more advanced model than TextRank, but TextRank is still a good solution if we don't have enough resources or if you have to run it really fast. Because, of course, it's much more faster when any of the neural networks. But of course, it depends on the size of input documents. I suppose what if you have some documents in size of, well, for example, a full dump of Wikipedia, Well, in which case, well, text rank will be a poor choice, but I suppose what all models will be a poor choice if you want to summarize the full Wikipedia into, well, small summary. And again, it still look like a very strange task because it's highly unlikely that we can extract some useful information from with such big text. So, well, here we import our summarizer, what are based on BERT model, and try to summarize our text again. And of course, it's handles some kind of the main idea of a text. So it's what's about Mary Jane, what who don't want to eat her breakfast. Well, again, we can vary our parameters of summarization. So almost like in all previous scenarios. Well, to sum up, we have two tasks in our summarization: abstractive summarization and extractive summarization, which are kind of similar because we evaluate both of these tasks with the same metrics, but we solve a different task because for abstractive summarization, we want to generate our summary, and for extractive summarization, we want to extract some sentences or words to create a new summary. Well, one could ask, do we still need all the summary techniques after the ChatGPT? And what we can do in summarization after the ChatGPT? So answer is simple. Yes, ChatGPT and similar models could generate very good summaries, and also could solve a lot of sequence-to-sequence task with very high quality results. But we still have a lot of different open problems and open issues in summarization task. For example, hallucination detection, some fast and robust summarization, and so on and so on. For example, ChatGPT, of course, didn't solve the hallucination problem, so we still have it in ChatGPT or some big generative models like, well, OpenAI DaVinci, GPT-3, and so on and so on. And of course, in most cases, some companies want to have their own summarization model, what will be fine-tuned on their data, maybe on their closed data sets. So they couldn't afford to use something like well, cloud-hosted GPT-like models. So there are still a lot of things to what one can do in summarization field. Even after all these big and very powerful models. So, well, that's all for today. I suppose what the next time we will briefly talk about some techniques to faster model inference and model training, something like pruning, quantization, knowledge distillation, and something like that, or maybe some even some combined methods, and maybe also speak about some more advanced topics. Well, that's all for today. Thank you for your attention. And if you have any questions, well, feel free to ask.
No, no questions, I guess. Thank you.
Well, thank you. Well, have a good day.
Have a good one.